So with this kind of taken care of, we're now in a position to say something that is probably going to seem pretty interesting to people. This is kind of a big result, or a big step. It's kind of one of the major things. So here it is. Since we know now that axiom systems have to be a computably enumerable sets, we can now kind of fully say that why, for any axiom system gamma, proofs for that axiom system, the set of all things which have proofs, is a computably enumerable set. This is a computably enumerable decision problem. We can finally show that now. So let's talk about why that is. It's a little complicated, the construction, but it's also not, I don't think. Given what we've said so far, it really isn't that complicated. But it's still kind of complicated. So since gamma is computably enumerable, we said that. That's built into the definition now. Any axiom system is computably enumerable as a set. We have a machine which can confirm in finite time that a well-formed formula is in the axiom set. So I'm using that I'm going to use two different definitions of computably enumerable. Here I'm using the definition that says it's computably enumerable if there exists a Turing machine that eventually confirms the yes answers. So I have a machine on the ready that's going to be looking at sentences and telling me whether or not they are in the axiom system. So that's one thing that I have. We can also computably enumerate all of the sentences, right? We can do that because we can computably enumerate all of the whiffs, because the set of all, the language of mathematics is definable by a formal grammar, we said, and formal grammars are equivalent to being computably enumerable. So we can have a machine computably enumerate over all of the well-formed formulas, and being a sentence just amounts to checking if all the variables are within quantifiers. So we can, of course, computably enumerate over all sentences just as easily. So we can computably enumerate over all sentences. Thus, we can computably enumerate over all pairs of sentences using the snake thing, or dovetailing if you're still wanting to sound smarter. Remember the snake thing? I copied and pasted it over from the video where I defined it. This is the snake thing. The snake thing is basically if you want to basically computably enumerate over pairs of infinite sets, you can basically just move like this. Basically, here's 1, 1, here's 1, 2, here's 2, 1, here's 2, 2, here's 3, 3, 1, 3, 2, 3, 3. Basically, if you just zigzag like this back and forth, then you kind of obtain an algorithmic way to move through every possible pair of two different computably enumerable things. And so I can do that. And if I do that, then I can computably enumerate over all pairs of sentences. Now here's the thing. If we can do that, then we can actually computably enumerate over all of the triplets, over all the 3 tuples, by doing the snake thing again, but with pairs as one axis and single sentences on the other. So before, we were basically looking at so I wrote here computably enumerable thing number 1, computably enumerable thing number 2. In the step that I just did, in order to computably enumerate over all pairs, I was looking at sentences, phi, and then other sentences, phi. But this method, this snake thing method, works for any computably enumerable set. So I'm just going to replace one of them. I'll keep this one as individual sentences, but over here I'll put my new computably enumerable set, the pairs. I can just have index all the pairs. And now if I do the snake thing over this thing, then I get all triplets, right? I get basically stuff like this. Right? But that's of course just, that's the same thing as just x, y, z. So I get all triplets. And then I can do it again. I can replace this with all 3 tuples. I can do the snake thing over here. And then I can put 4 tuples, and then 5 tuples, and 6 tuples. And when I say doing it in this order, what I'm really saying is that if you want like a 7 tuple, then what you're going to have to do is you're going to have to run a subroutine which enumerates the 6 tuples. And then that subroutine executes a subroutine for the 5 tuples, and then it goes down. It's a recursive algorithm that I'm describing here. It's a recursive algorithm where each sub-algorithm is doing a snake thing over the one inside of that, with another computable enumerable set of sentences phi. And so with all of that said, what I'm really doing here is I'm coming up with a machine that can enumerate over all the k tuples for any k. So I can now computably enumerate all of the k-tuples of sentences by doing the snake thing recursively in this way. Recursively in the way that computer scientists actually know recursive. It's like boxes inside of boxes kind of thing. But now I can computably enumerate all the k-tuples. Then what do I do after that? Well, then I just computably enumerate over everything, right? I can interlace the computations. I can computably enumerate. I can basically compute by doing the first single sentence, and then like the next, I can interlace all of them, and then I can computably enumerate over all sequences of sentences of every length. So all of this is to say that, and I haven't used this at all yet. The axiom thing, I haven't used all of it. If I kind of look at all this together, what I'm really justifying here is that I can computably enumerate over every single possible finite sequence of sentences. In other words, we can computably enumerate. This is all to say, can computably enumerate all finite sequences of sentences, i.e. all possible proofs. I can computably enumerate over all possible proofs. And so if I can computably enumerate over all possible proofs, all finite sequences of sentences of every length, and I can computably enumerate whether or not single elements of those sequences are axioms, then I can certainly check to see that modus ponens is satisfied for any non-axiom. Well, not really for any non-axiom, because I can't confirm that it's a non-axiom, but what I can do is I can kind of look for things that justify it, and eventually, if all of them are axioms, then I can kind of think about a machine that will eventually tell me that I have, wait for it, a valid proof. So I might not be able to check that things aren't axioms, but I can construct a machine using the machine that checks to see that it's a valid axiom. I can construct a machine that, if it's a valid proof, it will halt and accept. And thus, doing that, I can computably enumerate a list of all valid proofs. And if I can computably enumerate a list of all valid proofs, then it's one extra step to just pluck the final sentence out of every valid proof. And if I can computably enumerate all valid proofs, then I can computably enumerate all sentences which have proofs by just plucking out the last line of each one. And therefore, I am generating a set of every single thing that has a proof. And that was obviously a lot, so I drew a really informal picture over here to just kind of explain, make sure that everybody gets what I'm really arguing here in kind of shorthand. So we have three kind of machines that are doing stuff. Here's machine one. Machine one is generating all possible proofs. It's the thing in the red here that was generating every possible sequence of sentences of every possible length. It's going to just do that forever, and it's going to make them all. You got machine two operating on that list, and it's doing it in like maybe every other step, right? Maybe steps 1, 4, 7, 10, 13, like every fourth step, or I'm basically trading like computing power. Like I'm kind of running these three machines in parallel. So steps 1, 4, 7, 10, 13, it's generating the list of possible steps, possible proofs. Steps 2, 5, 8, 11, it's running the machine that checks to see that each of these is a valid proof, and then it's adding those to its own list. So it's going for it's pruning the possible proofs, that list, and generating its own list of valid proofs. And then there's machine 3, which has a very easy job. It's just plucking the very last sentence out of every one of these valid proofs and generating a sequence of every sentence which has a proof. In other words, it's generating the sequence of all sentences phi such that gamma proves phi, and therefore that's literally the set proofs of gamma, and therefore we have a computably enumerable algorithm for listing off all the proofs. In other words, to kind of summarize all of this, I have a machine that can generate a full list eventually of every single statement that has a proof. And that is going to be very significant. In other words, this is in Re. This is a decision problem, and it's a recursively enumerable decision problem. And the consequences of that, well, I mean, it's probably clear that there will be some. So stay tuned for that.